did you have actually, sorry if I did not follow fully, I thought primordially that there are physical gravitons as well, right?
When you say physical graviton, do you mean the?
Well, you mentioned biceps, so that people say, imprints of gravitational waves.
Yeah.
So that means there are physical gravitons.
Okay.
But I think you treated the gravitons as virtual, right? It's a virtual correction to the propagation of the photon.
Yes.
But if there are physical gravitons around, how does that affect the photon? They can scatter, right?
You mean the physical graviton during the primordial inflation interacts with the photons?
Yeah, I'm just linking to the rudimentary knowledge that I have. That people are after the B mode. Why? Because the gravitational waves early on will put an imprint.
Yeah. But this imprint will be the photon on the cosmic microwave background. I mean, on the surface of last scattering interact with.
Right. But it means that before that there are gravitational waves, which means there are physical gravitons.
Yeah.
So if I go all the way back, you did not seem to imply that your photons can scatter off physical gravitons.
No, it's a different thing. Vacuum polarization is different from the effects you just mentioned. It's different.
So my question is therefore, how large would that be? Because you also avoided initial conditions, etc., etc.
Yes, I think the effects you mentioned is about the GH square, because we do not measure this one. This one is about roughly about, if we assume single scale. Single scale inflation, then the order you just talk about, the effects you just talk about, you mean the dynamic graviton 1 imprint at the cosmic microwave background, interact with the photons. The order is about the GH square, and this is about this big. But the effects, if you say, okay, you do this kind of calculation, the vacuum polarization, and can you measure this kind of effects on the cosmic microwave background? Then the thing is, okay, you have an Einstein equation. Okay, you might say, okay, let me put into this part, the source term. Okay. Here is one loop result. Here the other G. So basically it's much smaller. It's about 2 loop result. Not 2 loop, you will give you the 2 GH square. This kind of effects, if you want to say, okay, how big of this effects, which can be imprinted on cosmic microwave background, I would say it's pretty small.
Okay.
I think I would ask you, what diagram do you think would correspond to the process you're talking about? I would claim that the process you're talking about, when real particle production occurs, the way that she mentioned in the first part of the talk, that is exactly taken account of by looking at vacuum polarization. If you don't think so, what extra diagram do you think would be necessary?
Well, I didn't do the calculation, but just saying that if you worry about the loop effect, and also we're talking about when things were, actually I didn't quite understand that you can get away with the initial condition, the late time statement.
Oh, you mean this initial state correction, you mean? Or what kind of initial condition?
Well, you said your result is only valid for late times,
yes.
And you did not really deal with, I don't have intuition for inflation, I'm sorry.
Oh, okay, consider the Schwinger effect. So forget about inflation, look at flat space, you establish a constant electric field from one end of the universe to the other. We all agree that physical electron-positron pairs are created in that situation, yes? Is that okay? Do you agree?
Okay. I'm I'm only exposing my ignorance, but I'm just asking, and also trying to.
Well, no, it's a good question. It's an excellent question, and it gets right to the fundamentals of doing these calculations. So forget all about inflation. Let's go to flat space, quantum electrodynamics, just electrons and photons. However, now, instead of having zero electric field as our background, we have a background electric field that goes in the z direction, and it's exactly constant, any magnitude you want, it doesn't matter how small, and it goes from one end of the universe to the other. Okay? That process, as you know, was studied by Julian Schwinger way back in a famous paper, and he concluded that no matter how small the electric field is, electrons and positrons are pulled out of the vacuum because making the electric field small just makes the potential small, but it's a linear potential, and sooner or later they can tunnel the distance that they have to make up their rest mass energy, and they will emerge and become real particles. So everybody admits that that process is true, that process actually occurs. If you are studying the effect of that process, what diagram do you think you would consider? I claim that the diagram you would consider is exactly the same as the usual vacuum polarization diagram in quantum electrodynamics, namely photon comes in, virtual electron-positron pair goes around, comes back together again, goes to a photon. That's exactly the diagram that you would consider, and that diagram will encapsulate that particle production process. If you believe me about that, then that's exactly what she's reporting on there. No difference at all. Namely, she convinced you that in the early universe, because the energy-time uncertainty principle changes, gravitons will be pulled out of the vacuum, just like in the Schwinger effect, virtual electron-positron pairs get pulled out of the vacuum. And the diagram that you would consider to study that process is just exactly vacuum polarization. And it's right to consider that because that will include the effect of the particles being in that funny background will change the fermion propagators so that they include the effect of physical fermions emerging from the vacuum. That will exactly describe it correctly. And if you don't believe that, identify what other diagram you would want. It isn't one with external fermions present because in the initial state they aren't present. There are none initially, nor are there any initially present in initial gravitons present in the universe that she's considering. It really is the vacuum polarization. That's the right way to include this effect.
Well, you said gravity is now perturbative, but okay, I guess my question is closer to the initial condition. Just
that's also a fascinating question. Initial conditions certainly make a difference, no question at all about it. But the thing that grows with time is the continual production of gravitons. So we can't know the initial conditions. We weren't there. We don't have any experimental observation of it. But we can distinguish the effect, the constant effect of changing the initial conditions from the secular effect of that you wait longer, more gravitons get produced. So that's the one that we can calculate reliably.
okay, I was in part just to ask out of curiosity because our students rarely ask questions, so it was a demonstration.
You get an A.
Oh, okay. I pass.
A plus. Those are the best questions.
Okay. Any student questions or non-student questions? It's only mostly students today, so. Oh, okay.
The last second slide, you write down 3 reasons for non-invariant counterpoint sources.
Louder, I cannot hear you.
In the last second slide, you write down 3.
This one?
Yes, 3 reasons for non-invariant counterpoint. So does this 3 reasons also imply that break is invariant?
Yes, because you have this pick up the spatial iteration. See, when you have this extra piece, that means you might have extra piece of temporal part or the extra piece of purely spatial part. Okay, so you break the disintegrants. Yeah.
Okay, any further questions? So I don't see any further questions. Let's thank Professor Miao again.